All right, buckle up, everyone, because today we're going deep, like really deep.
Into the churning waters around coastal headlands?
Exactly. You know those dramatic rocky points that jet out from the coast? Ever notice how the water around them can be wildly different?
Yeah, like 1 minute you've got currents that could sweep you off your feet, and the next, it's calm as a bathtub.
Precisely. So what's the deal with those headlands and their impact on tides and currents? Well, to guide us, we've got a real gem.
Tidal Dynamics and Dispersion Around Coastal Headlands, a doctoral thesis by Richard P. Signal.
MIT, no less. And the Woods Hole Oceanographic Institution.
The guy knows his stuff, that's for sure.
Okay, so break it down for us. What's Signal diving into with this thesis?
So it's about way more than just the tide going in and out. It gets into the nitty-gritty of how water actually moves around these headlands.
Okay, I'm intrigued.
He's not just looking at the overall current, but like what happens to individual parcels of water.
Individual parcels.
Yeah, imagine like tracking a single drop of water as it gets tossed around by the tides. To do this, he uses something called shallow water equations. Pretty complex stuff.
Sounds intense. Shallow water equations.
Yeah, some pretty heavy physics, but the gist is it helps us understand those hidden movements beneath the surface.
So there's this whole hidden dance going on beneath the waves.
Precisely. And it turns out that dance has a huge impact on things like how pollutants spread, which is obviously a major concern for coastal environments.
Right, makes sense. A swirling current could spread pollutants far and wide.
Exactly. Or how marine life get transported, you know. Those currents can be like underwater highways.
Like little fish hitching a ride on a tidal roller coaster.
Exactly. Now, Signal uses a 2D model in his thesis to simplify things, make it easier to wrap our heads around. He's assuming the water is well mixed, which isn't always the case in the real world. But it's surprisingly accurate for understanding the big picture.
Okay, so a simplified model, but still relevant to what's going on out there in the ocean.
Absolutely. And especially near the headland tip, that's where things get really interesting. Like, that's where all the action is.
Okay, I'm hooked. Tell me more about what's happening at the tip of the headland. All right, so we've got our virtual headland, tides are rolling in, waves are crashing. What's the picture Signal paints for us? What's going on?
Okay, so picture this, right? The tide comes surging in, slams into this wall of rock, the headland.
Okay, I can visualize that.
And the water, it can't just go through the rock, so it's got to go somewhere.
It has to move around?
Exactly. So it starts to peel away, that's the word Signal uses, from the headland.
Peel away?
Yeah, like imagine peeling an orange. It kind of creates this like swirling motion.
Okay.
And that, my friend, is the birth of a startup eddy.
A startup eddy? Is that like a mini whirlpool?
You got it. It's like this little vortex just spinning away there.
Wow. So the water is not just flowing past, it's getting spun off the headland.
Exactly. And as the tide keeps pushing more water in, this eddy, it just keeps wrapping up.
Wrapping up.
Yeah, like it's almost like, those spiral patterns you see in nature?
Like a seashell.
Yeah, exactly. Except this one's made of water and it's constantly evolving. But here's the thing. It's not just the shape of the headland that dictates all of this swirling.
It's not. What else is there?
The speed of the water, how fast the tide is coming in, that plays a huge role too. And then there are these other factors like, the aspect ratio of the headland.
The what now? Aspect ratio.
Basically like how steep its sides are.
Oh, okay. So like a gradual slope versus a sheer cliff.
Exactly. And then there are things like the frictional Reynolds number and the Kulik-Carpenter number, but those are probably best left for another deep dive.
I think my head might explode if we get into those right now.
Probably wise, yeah. But basically, all of these factors, they all come together to create this incredible dance of physics that determines how these eddies form and behave.
It's amazing to think that something as simple as a rocky outcropping can create these complex underwater patterns.
It really is. And it just goes to show the ocean is full of surprises.
So we've talked about these eddies forming, but what's the real-world impact? Why should we care about these underwater whirlpools? So we've talked about these eddies forming, but what's the real-world impact? Why should we care about these underwater whirlpools?
Well, for starters, remember how we talked about pollutants?
Yes, swirling around in those eddies?
Yeah, exactly. Imagine an oil spill near a headland.
Uh-oh.
Instead of the oil being carried away by the tide, it could get trapped in those eddies, making cleanup a nightmare.
So instead of just following the current, cleanup crews would have to account for these swirling pockets of oil.
Precisely. It gets even more interesting when you think about marine life.
Right, like those little fish hitching a ride we talked about.
Exactly. Some creatures might get caught in those eddies, for better or for worse. Like, it could be a buffet for them if plankton concentrates there.
Oh, like an all-you-can-eat plankton buffet.
Yeah. But for other creatures, it might disrupt their migration or breeding patterns. It's like a roll of the dice.
Wow, it's like these eddies are shaping the underwater world in ways we're only just beginning to understand.
Totally. And what's even crazier is how the journey of a single drop of water, what Signal calls Lagrangian residual velocity, can be totally different from the overall flow.
So even if we know which way the tide is going, a single drop of water might be doing its own thing.
Exactly. It's like, yeah, if you look at a river, you see the current, right? But each drop of water within that current is on its own little journey.
Mind-blowing. It makes you wonder, where does a single drop of water end up after being caught in one of these headland eddies?
Right. Like, does it ever break free? Does it get stuck there forever? So many questions still to answer.
It really highlights how much we still don't know about the ocean. Well, that's a mind-bending thought to leave us with. Next time you're looking out at a headland, picture those swirling eddies beneath the surface and the secret journeys of those tiny drops of water. Thanks for diving deep with us.